Good evening, thoughtful traveler, and welcome to this quiet corner of the night. Whether you've come to gently close your day or simply rest your mind beneath the hush of calm curiosity, I'm so glad you're here. Tonight, we're not chasing formulas or solving problems. Instead, we're drifting softly into one of the most beautiful ideas ever imagined, a way of seeing time, space, and the universe that changed everything. Einstein's theory of relativity. Before we begin, feel free to share in the comments where in the world you're listening from. There's something comforting in knowing that, even as we lie scattered across oceans and cities, we're connected in this peaceful pause, together in thought. I invite you to subscribe so we can share many more quiet journeys like this. Now, let us begin. Chapter 1: The Curious Mind of Young Einstein. In the quiet town of Ulm, in the south of Germany, during the year 1879, a child was born who would eventually reshape our understanding of the universe. His name was Albert Einstein. At first glance, there was nothing remarkable about him. As a young boy, he spoke slowly and often appeared withdrawn. He was contemplative, quiet, and deeply absorbed in his own thoughts. While some saw this as a concern, it was the early sign of a mind that was busy observing, questioning, and making sense of the world in a way few others could. One of his earliest formative moments came when he was about 5 years old. He was given a small magnetic compass. Turning it in his hands, he noticed that no matter how he moved, the needle always pointed in the same direction. This invisible force fascinated him. How could something act across space with no strings, no contact, and no obvious source? That compass would stay with him for years, not just physically, but as a symbol of hidden forces and unanswered questions. School did not suit him. His teachers saw him as a dreamer, someone who didn't follow directions or think in the expected way. He found their rigid methods stifling, while others were satisfied to memorize and repeat. Einstein wanted to understand. He loved music and played the violin with real passion, but it was the quiet beauty of mathematics and the logical elegance of geometry that truly captured his attention. As he grew older, he read widely. He explored the ideas of philosophers, scientists, and mathematicians. He was especially drawn to the mysteries of space, time, and motion. He liked problems that had no easy answers. His mind wasn't content with surface explanations. It sought out the fundamental rules beneath everything. At 15, Einstein's family moved to Italy, leaving him behind in Germany to finish his schooling. Unhappy and isolated, he eventually left school altogether. He later enrolled in a school in Switzerland and applied to the Swiss Federal Polytechnic in Zurich. He failed the entrance exam the first time, but passed on the second attempt. Even after entering, he was not viewed as an exceptional student by his professors. He often skipped lectures and spent time studying topics that interested him personally. What fascinated him more than anything was light. He imagined what it would be like to ride alongside a beam of light. If a person could somehow travel at the speed of light, what would they see? Would the wave of light freeze? Would time behave differently? These were not idle thoughts. They were serious explorations into the nature of reality. And they pointed towards something radical, that time and motion might not be what people assumed them to be. After graduating, Einstein struggled to find a teaching post. He eventually took a job at the Swiss Patent Office in the city of Bern. There, in the routine of reviewing applications for electrical devices, he found space to think. His job was quiet, and his work left his mind free to roam. During this time, he began developing the ideas that would become his theory of special relativity. He thought about how observers moving at different speeds might measure events differently. He thought about how time might not be fixed, but relative. He combined this with ideas from James Clerk Maxwell, whose equations showed that light travels at a constant speed, regardless of the motion of the observer. This idea did not fit with the physics of Isaac Newton, which had dominated scientific thinking for over 200 years. Newton's universe treated time as absolute, flowing evenly for all observers. Einstein suspected that this couldn't be true. What if time itself changed, depending on how fast someone was moving? In the year 1905, while still working at the patent office, Einstein published 4 groundbreaking papers. One of them introduced the special theory of relativity. In it, he proposed that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is constant, no matter how fast an observer is moving. From this, astonishing consequences followed. Clocks moving at high speeds would tick more slowly compared to stationary ones. Objects would appear to contract in the direction of motion, and perhaps most famously, energy and mass were shown to be equivalent, expressed in the simple and now iconic formula E equals mc squared. The world Einstein revealed was not the one most people imagined. It was a world where time could stretch and space could warp. A world where motion affected measurement and where different observers could experience the same event in different ways and both be right. But Einstein was not trying to be radical. He was trying to make sense of something that didn't fit within the old framework. He once remarked, "I have no special talent. I am only passionately curious." And it was that curiosity, more than anything else, that drove him to challenge centuries of established thinking. The image most people have of Einstein is of the older man, wild hair, chalk in hand, lost in equations. But before that, there was the boy with the compass, the teenager frustrated by rules, the young man thinking about light while reviewing patents. His story begins not with greatness, but with questions. And it was the courage to ask those questions, quietly, persistently, that made all the difference. Chapter 2: Newton's Universe and its Limits. Before Albert Einstein challenged the foundations of space and time, there was Sir Isaac Newton. Born in the year 1643 in England, Newton gave the world a framework for understanding the physical universe that would last for more than 2 centuries. His theories, brought order to a previously chaotic view of nature. Through mathematics, he explained motion, gravity, and the behavior of celestial bodies. In 1687, Newton published Philosophia Naturalis Principia Mathematica, one of the most influential scientific works ever written. In it, he described a universe governed by natural laws. His laws of motion and universal gravitation explained why apples fall from trees, why the moon orbits the Earth, and why planets trace predictable paths around the sun. Newton's universe was logical, precise, and deeply appealing. It worked like a great clock, a mechanism of perfect regularity. Time was absolute, space was fixed, forces acted across empty distances with mathematical clarity. According to this view, the same physical principles applied everywhere, from falling objects on Earth to the orbits of distant planets. This vision held tremendous power. It could predict eclipses, calculate the flight of cannonballs, and explain the tides. For scientists, engineers, and philosophers, it felt like the universe had finally revealed its underlying structure. At the core of Newton's system were a few key assumptions. One of them was the idea of absolute time. Time, Newton believed, flowed at a constant rate, independent of everything else. Whether someone was standing still or flying through space, a second was always a second. It didn't change. It was universal. Another assumption was the nature of space. Space was imagined as an empty container, a passive stage on which events happened. Things could move through it, but space itself did not change. It had no texture, no flexibility, no influence over what happened within it. It was simply the background. These ideas made sense in the context of everyday experience. When walking through a room or watching a pendulum swing, time and space appear steady and predictable. Newton's theories matched that common sense. But by the 19th century, deeper questions began to emerge. Scientists studying electricity and magnetism discovered that light behaved like a wave. Waves, as commonly understood, needed something to travel through: air for sound, water for ripples, or a solid for vibrations. So what was light traveling through in the vast emptiness of space? To solve this, physicists proposed the existence of a mysterious substance called the luminiferous ether. This invisible medium was said to fill all of space, providing the necessary backdrop for light to propagate. However, experiments designed to detect the motion of the Earth through this ether failed. Most famously, the Michelson-Morley experiment of 1887 showed no difference in the speed of light, regardless of the Earth's motion. This puzzled scientists. If light was a wave and waves needed a medium, why couldn't this medium be found? Even more confusing was that light always seemed to travel at the same speed, no matter how fast the observer was moving. In Newton's system, if someone moved toward a sound, the pitch and speed would change. Yet for light, nothing changed. Its speed remained constant. This fact didn't fit easily with Newton's framework. It pointed toward a problem, not with light, but with the assumptions about time and space. Still, the Newtonian model remained dominant. It worked so well for so many problems that it was hard to let go. But Einstein was willing to question it. He considered the implications of light's constant speed. If two observers were moving relative to each other and both measured the same speed for a beam of light, something else had to give. Either the light was behaving in an impossible way, or time and space themselves were not as fixed as Newton believed. Einstein began to explore the consequences of abandoning absolute time. He asked, what if time moved differently for observers in motion? What if space could stretch or contract, depending on how fast one traveled? These questions led him toward a radically different view of the universe. In this new view, time was not a universal rhythm. Instead, it was personal, dependent on motion. Clocks moving at different speeds could tick at different rates. Space was not a passive backdrop, but something dynamic. The faster one moved, the more it transformed. Einstein's willingness to reimagine the fundamentals marked a turning point. He did not discard Newton's work, but extended it. He once wrote, "Newton, forgive me," acknowledging that his own theories built upon those that came before. Newton had revealed the laws of motion and gravity. Einstein would reveal the deeper structure of reality, how space and time were part of a single fabric. The limits of Newton's universe were not failures, but invitations. They opened the door for a new kind of thinking. Newton had mapped the visible world with remarkable clarity. Einstein would explore the invisible dimensions beneath it. As scientific instruments became more precise and experiments reached further into the extremes of speed and distance, it became clear that Newton's laws were only part of the picture. They worked well at everyday speeds and scales. But in the realms of the very fast, the very massive, and the very distant, new rules were needed. Those rules would come in the form of the theory of special relativity, a theory that began not with measurements, but with imagination, not with laboratories, but with thought experiments. It was there, in quiet reflection, that Einstein began to replace the old framework with something more profound. From Newton's steady clockwork to Einstein's flexible space-time, physics was about to make a leap that would forever change how people understood reality itself. Chapter 3: The Birth of Special Relativity. At the start of the 20th century, physics stood at a crossroads. The successes of Newtonian mechanics were undeniable. Engineers used it to build bridges and machines. Astronomers used it to chart the orbits of planets and moons. It seemed, to many, that most of the great problems had already been solved. But quietly, a few oddities refused to fit. The speed of light, measured repeatedly in different conditions, always returned the same value. Whether the observer moved toward the light source or away from it, the result was unchanged. This defied common sense. In everyday life, the speed of a moving object is always relative. A train moves faster toward a person on the platform and slower if they're running alongside it. Why didn't light behave the same way? These puzzles left physicists uneasy. They tried to adjust their theories to fit the data, but nothing worked without adding complications or inconsistencies. Most accepted the contradictions as technical problems to be resolved later. Albert Einstein did not. Working at the Swiss Patent Office in the city of Bern, Einstein was far removed from the major centers of academic science. Yet he was thinking deeply about the same problems, and in a very different way. Free from the traditions and expectations of formal institutions, he had the freedom to follow ideas wherever they led. He took a simple approach. Instead of trying to patch the old system, he asked, what if we started with two basic principles? First, that the laws of physics are the same for all observers, no matter how fast they are moving, as long as their motion is steady. Second, that the speed of light is constant for all observers, regardless of their motion or the motion of the light source. These two assumptions were bold. At first glance, they seemed to contradict each other, but Einstein believed both were true, and he was willing to explore the consequences, no matter how strange they might be. What he discovered changed physics forever. In the year 1905, he published a paper titled On the Electrodynamics of Moving Bodies. In it, he introduced what would later be called the special theory of relativity. The word special referred to the fact that it applied to situations where motion is constant. No acceleration, no gravity, just simple movement through space. The theory showed that time and space were not fixed, universal quantities. They were relative. They depended on the motion of the observer. Einstein proved that if the speed of light must stay constant, then something else has to give. Time must stretch, space must shrink, mass must increase with speed. These were not philosophical ideas, they were mathematical consequences of the two starting principles. One of the most famous results was time dilation. According to the theory, a moving clock ticks more slowly than a stationary one. The faster it moves, the greater the difference. If a spaceship traveled at a speed close to that of light, time on board would pass more slowly compared to time on Earth. To the traveler, everything would seem normal. But when they returned, they would find that more time had passed for everyone else. Another result was length contraction. Objects moving at high speeds appear shorter in the direction of motion. This effect becomes noticeable only at speeds approaching the speed of light. In daily life, it's impossible to detect, but in high-energy physics, where particles move at incredible speeds, it becomes critical. The most famous equation to emerge from this theory was simple in form, but profound in meaning. E equals mc squared. This equation states that energy and mass are two forms of the same thing. A small amount of mass can be converted into a large amount of energy because the speed of light squared is an enormous number. This relationship would later help explain the energy released in nuclear reactions. Einstein's theory was not just a collection of effects. It represented a completely new way of thinking about the universe. Space and time were no longer separate entities. They were part of a single, four-dimensional structure known as space-time. And within this framework, motion reshaped experience itself. The implications were staggering. No longer could one say that two events happened at the same time for everyone. Simultaneity, the idea that events occur at the same moment everywhere, was revealed to be an illusion. What is now, for one observer, might be in the future or in the past for another, depending on their motion. These ideas were unsettling at first. They challenged intuition and common sense, but they explained the behavior of light. They resolved the contradictions in Maxwell's equations, and they were confirmed by experiments. In time, other scientists began to understand the power of Einstein's work. The theory of special relativity was tested, scrutinized, and ultimately accepted. It became one of the foundations of modern physics. And it all began with a thought experiment. A young man wondering what it would be like to chase a beam of light. What made Einstein different was not access to new data or tools. It was his willingness to trust logic over convention. He followed the consequences of his assumptions, even when they led away from the familiar. The birth of special relativity was not just a scientific breakthrough, it was a shift in perspective, a reminder that reality may not always match expectations, and that truth sometimes hides in places that defy tradition. It showed that deep understanding begins not with certainty, but with curiosity and the courage to ask what if. Chapter 4. Time dilation and the nature of time. Time feels constant. It flows from moment to moment with a steady rhythm. Clocks tick, the sun rises and sets, and we live our lives by the regular beat of seconds, minutes, and hours. This is the world as we experience it, structured, predictable, and linear. But Einstein's special theory of relativity challenged that view. According to his work, time is not universal. It does not pass identically for all observers. It can stretch, it can contract, it can behave differently depending on how fast one is moving. This strange behavior is known as time dilation. To understand time dilation, imagine two identical clocks. One remains stationary on Earth, while the other is placed aboard a spaceship traveling at a high speed through space. When the spaceship returns, the two clocks are compared. The clock that traveled at high speed will show that less time has passed than the clock that stayed behind. From the traveler's perspective, everything seemed normal. Their heart beat at the same rate. Their conversations occurred at the usual pace. But upon return, they find that more time has passed for the world they left behind. They have aged less. This is not a theory in the abstract. It is a measurable, physical effect. Time dilation has been confirmed in many experiments. One of the most striking examples involves particles called muons. Muons are created when cosmic rays strike the Earth's atmosphere. These particles decay very quickly, usually in a few millionths of a second. According to classical physics, they should not survive long enough to reach the surface of the Earth. But they do. Why? Because they are moving close to the speed of light. At such speeds, their internal clocks, so to speak, run slower. From our point of view, their decay takes longer. From their point of view, their journey is shorter. Both perspectives are correct within the framework of relativity. This effect also appears in technologies like GPS. The satellites that make GPS possible orbit the Earth at high speeds and at high altitudes. Both motion and gravity affect the passage of time for these satellites. Engineers must account for time dilation in the calculations. If they did not, GPS systems would become inaccurate within minutes. The clocks on satellites are constantly corrected to match the time measured on Earth. This reveals something profound. There is no single, absolute time. Instead, each observer carries their own time. These different clocks, moving or still, can fall out of sync, depending on the speeds involved. Einstein showed that time and space are linked. The faster someone moves through space, the more slowly they move through time. It is as if the universe grants a kind of trade-off. Motion through space reduces motion through time. This leads to a surprising conclusion. If a person could move at the speed of light, their passage through time would stop entirely. From their perspective, everything would happen at once. However, no object with mass can reach the speed of light. The closer it gets, the more energy it requires. At the speed of light, that energy would become infinite. Light itself travels this way, but it has no mass. The nature of time is not just a question for physicists. It touches everything. Time connects memory and identity. It creates the structure of cause and effect. We remember the past, live in the present, and anticipate the future. But relativity shows that these divisions are not as simple as they seem. In Einstein's universe, there is no universal now. Imagine two events, one happening on Earth and another on a distant star. Whether those events happen at the same time depends on the observer's motion. What is now for one person may be in the past or in the future for another. There is no privileged viewpoint from which time flows evenly for all. This challenges the idea of time as a straight, single path. Instead, time is part of a broader structure, woven into the very fabric of space. This combination of space and time is known as space-time. Objects move through it, not just in 3 dimensions, but 4. And just as space can be measured differently by different observers, so can time. One of the great strengths of Einstein's theory is its consistency. It does not allow contradictions. Every observer must agree on the outcome of events, even if they disagree on the order or timing. The laws of physics hold true in all frames of reference. This unity gives relativity its power. Time dilation is not something that contradicts reality. It is reality. It simply doesn't match our everyday experience because we do not move fast enough to notice it. But it is there, shaping every high-speed particle, every orbiting satellite, and every clock in motion. Einstein revealed that time is not a river flowing independently through the cosmos. It is more like a thread sewn into the movements of matter and energy. It bends, stretches, and responds to the way we move. This view of time alters how people think about aging, travel, and even the possibility of journeys to the stars. In science fiction, the concept of time dilation often appears in stories about long-distance space travel. A crew might leave Earth and return decades later, having only aged a few years themselves. While the dramatic versions are fiction, the physics behind them is real. Time dilation reminds us that our everyday experience is just one version of reality. Beneath it lies a deeper structure, less visible, but no less true. A structure where time is not a constant rhythm, but a variable, shaped by speed and motion. This discovery opened the door to even greater questions. If motion can affect time, what about gravity? Could the presence of mass and energy also warp time and space? Those questions would lead Einstein to the next step in his journey, a new theory that would reach beyond speed and motion to describe the very shape of the universe itself. Chapter 5: Length, Contraction, and the Speed of Light. In the world of classical physics, objects have a definite size. A meter stick is always 1 meter long. A train car stays the same length whether it's parked or speeding along the tracks. This seems obvious. Length appears to be constant, a fixed property of the physical world. But in the framework of relativity, this is no longer true. Just as time can slow down for objects in motion, space itself can shrink. This phenomenon is known as length contraction. And while it may sound like science fiction, it is a natural consequence of Einstein's theory of special relativity. To understand this, imagine two observers. The first is standing still beside a train track. The second is riding inside a train moving close to the speed of light. For the observer on the ground, the train appears shorter than it would if it were standing still. From their point of view, the faster the train moves, the more it contracts in the direction of motion. This contraction is not an illusion. It is a measurable, real effect, though only at extremely high speeds. In our everyday world, the difference is too small to notice. But in the world of high-speed particles and precise measurements, it becomes significant. From the perspective of someone inside the train, however, nothing seems different. They experience no change in length. Everything inside the train feels perfectly normal. That is the key to relativity. Each observer measures the world differently, depending on their state of motion. Both measurements are correct in their own frame of reference. Length contraction and time dilation are connected. They are part of the same transformation that occurs when an object moves quickly through space. If time slows down for the moving observer, space must also adjust in order to keep the speed of light constant for everyone. At the heart of this lies a simple but profound idea. The speed of light is the same for all observers. This constant speed, approximately 300,000 kilometers per second, does not change, regardless of how fast you are moving. Whether you run toward the light or away from it, whether the light source is stationary or moving, the result is the same. This defies intuition. In most cases, motion is additive. If you walk forward while on a moving walkway, your speed increases. But light is different. It breaks the rules of classical addition. It moves independently of the motion of its source or observer. To preserve this constancy, space and time must become flexible. They adjust themselves so that light's speed never changes. If time slows down for a fast-moving object, then distances must also contract in order to keep everything consistent. Mathematically, this is described by the Lorentz transformations, which relate the space and time coordinates of one observer to those of another moving at a constant speed. These equations replace the simple assumptions of classical mechanics with a new structure that honors the invariance of light. The effects of length contraction have been confirmed in particle accelerators. When subatomic particles like protons or muons are accelerated to near light speeds, their behavior matches the predictions of relativity. Their lifetimes increase, their dimensions contract. They move through space and time differently than slower particles. This understanding is not just theoretical. It plays a role in designing machines that study the building blocks of matter. Without relativity, these machines would not work correctly. Engineers and scientists rely on Einstein's equations to account for the changes that occur at high velocities. But why does length contraction only occur in the direction of motion? Relativity treats space and time as part of a unified structure. When an object moves, only the direction in which it travels is affected. Just as motion through space changes the flow of time, it also alters spatial dimensions, but only along the path of motion. This ensures that the speed of light remains constant in every direction and for every observer. This idea reveals how deeply space and time are linked. They are not separate ingredients in the recipe of the universe. They are part of a single continuum. What one observer sees as a long distance and short duration, another may see as a short distance and long duration. There is no single answer that applies to all. Only relationships between observers matter. Length contraction has philosophical implications as well. It challenges the notion of objectivity. If the length of something depends on how it is measured, then reality itself becomes frame-dependent. There is no true size, only the size relative to the observer's motion. This does not mean reality is uncertain. Relativity is precise. It gives exact predictions that match observations. But it shows that certain features of the world, like length and time, are not absolute. They belong to a dynamic, relative system. The speed of light plays a central role in all of this. It is more than just a fast number. It is a boundary. Nothing with mass, can reach or exceed this speed. As objects accelerate closer to the speed of light, they require more and more energy. Their mass effectively increases, and time and space deform more dramatically. At the speed of light, length contraction becomes complete. From the perspective of a photon, the distance between any 2 points becomes zero. The concept of time disappears. But again, this is not a frame that any object with mass can ever reach. It exists only as a mathematical idea, helping define the edges of what is physically possible. The constancy of the speed of light reshapes our understanding of motion. It forces us to discard old assumptions and embrace a new geometry of space-time, one where events and measurements depend on movement, and where observers in different states of motion live in subtly different realities. Einstein's insight was to see this not as a problem, but as the natural order of things. He did not try to force light to behave like everything else. Instead, he reimagined everything else so that light's behavior would make sense. Length contraction is just one part of that picture. Together with time dilation, it shows how motion weaves its influence through both space and time. It reminds us that the universe is not fixed in place. It responds. It shifts. It flows with speed. This flexibility, once hidden beneath layers of assumption, is now one of the most important truths in modern science. It opens the door to a universe far stranger and more beautiful than one governed by rigid, absolute rules. Chapter 5. Length contraction and the speed of light. In the world of classical physics, objects have a definite size. A meter stick is always 1 meter long. A train car stays the same length, whether it's parked or speeding along the tracks. This seems obvious. Length appears to be constant, a fixed property of the physical world. But in the framework of relativity, this is no longer true. Just as time can slow down for objects in motion, space itself can shrink. This phenomenon is known as length contraction. And while it may sound like science fiction, it is a natural consequence of Einstein's theory of special relativity. To understand this, imagine 2 observers. The first is standing still beside a train track. The second is riding inside a train moving close to the speed of light. For the observer on the ground, the train appears shorter than it would if it were standing still. From their point of view, the faster the train moves, the more it contracts in the direction of motion. This contraction is not an illusion. It is a measurable, real effect, though only at extremely high speeds. In our everyday world, the difference is too small to notice. But in the world of high-speed particles and precise measurements, it becomes significant. From the perspective of someone inside the train, however, nothing seems different. They experience no change in length. Everything inside the train feels perfectly normal. That is the key to relativity. Each observer measures the world differently, depending on their state of motion. Both measurements are correct in their own frame of reference. Length contraction and time dilation are connected, They are part of the same transformation that occurs when an object moves quickly through space. If time slows down for the moving observer, space must also adjust in order to keep the speed of light constant for everyone. At the heart of this lies a simple but profound idea. The speed of light is the same for all observers. This constant speed, approximately 300,000 kilometers per second, does not change, regardless of how fast you are moving. Whether you run toward the light or away from it, whether the light source is stationary or moving, the result is the same. This defies intuition. In most cases, motion is additive. If you walk forward while on a moving walkway, your speed increases. But light is different. It breaks the rules of classical addition. It moves independently of the motion of its source or observer. To preserve this constancy, space and time must become flexible. They adjust themselves so that light speed never changes. If time slows down for a fast-moving object, then distances must also contract in order to keep everything consistent. Mathematically, this is described by the Lorentz transformations, which relate the space and time coordinates of one observer to those of another moving at a constant speed. These equations replace the simple assumptions of classical mechanics with a new structure that honors the invariance of light. The effects of length contraction have been confirmed in particle accelerators. When subatomic particles like protons or muons are accelerated to near light speeds, their behavior matches the predictions of relativity. Their lifetimes increase, their dimensions contract. They move through space and time differently than slower particles. This understanding is not just theoretical. It plays a role in designing machines that study the building blocks of matter. Without relativity, these machines would not work correctly. Engineers and scientists rely on Einstein's equations to account for the changes that occur at high velocities. But why does length contraction only occur in the direction of motion? Relativity treats space and time as part of a unified structure. When an object moves, only the direction in which it travels is affected. Just as motion through space changes the flow of time, it also alters spatial dimensions, but only along the path of motion. This ensures that the speed of light remains constant in every direction and for every observer. This idea reveals how deeply space and time are linked. They are not separate ingredients in the recipe of the universe. They are part of a single continuum. What one observer sees as a long distance and short duration, another may see as a short distance and long duration. There is no single answer that applies to all. Only relationships between observers matter. Length contraction has philosophical implications as well. It challenges the notion of objectivity. If the length of something depends on how it is measured, then reality itself becomes frame-dependent. There is no true size, only the size relative to the observer's motion. This does not mean reality is uncertain. Relativity is precise. It gives exact predictions that match observations. But it shows that certain features of the world, like length and time, are not absolute. They belong to a dynamic relative system. The speed of light plays a central role in all of this. It is more than just a fast number. It is a boundary. Nothing with mass can reach or exceed this speed. As objects accelerate closer to the speed of light, they require more and more energy. Their mass effectively increases, and time and space deform more dramatically. At the speed of light, length contraction becomes complete. From the perspective of a photon, the distance between any 2 points becomes zero. The concept of time disappears. But again, this is not a frame that any object with mass can ever reach. It exists only as a mathematical idea, helping define the edges of what is physically possible. The constancy of the speed of light reshapes our understanding of motion. It forces us to discard old assumptions and embrace a new geometry of space-time, one where events and measurements depend on movement, and where observers in different states of motion live in subtly different realities. Einstein's insight was to see this not as a problem, but as the natural order of things. He did not try to force light to behave like everything else. Instead, he reimagined everything else so that light's behavior would make sense. Length contraction is just one part of that picture. Together with time dilation, it shows how motion weaves its influence through both space and time. It reminds us that the universe is not fixed in place. It responds, it shifts, it flows with speed. This flexibility, once hidden beneath layers of assumption, is now one of the most important truths in modern science. It opens the door to a universe far stranger and more beautiful than one governed by rigid, absolute rules. Chapter 7: Simultaneity and the Order of Events. In daily life, time seems straightforward. One event happens, then another. A cup falls, it breaks. Someone reacts. These events unfold in a clear sequence: before, during, after. We assume that this sequence is the same for everyone, everywhere. But Einstein's theory of special relativity challenges this deeply held belief. It tells us that simultaneity, the idea that two events occur at the same moment in time, is not absolute. It depends on the observer's frame of reference. Events that seem simultaneous to one person may not appear that way to another if they are moving relative to each other. To see how this works, imagine a long train moving along a track. A lightning bolt strikes the front of the train and another strikes the back. At the same time, from the point of view of someone standing on the platform beside the track. That person, standing still, sees both flashes at once. But now imagine someone sitting in the middle of the train. As the lightning strikes both ends, the train is moving forward. From their point of view, the flash at the front of the train must travel farther to reach them than the flash at the back. Since both flashes of light travel at the same speed, the one that reaches them first must have occurred earlier. They will conclude that the two strikes did not happen at the same time. Neither observer is wrong. Each is simply measuring events from a different perspective. This difference is not about perception or delay. It is not an illusion. It is a real, measurable disagreement about the timing of events. In Einstein's universe, simultaneity is not universal. It is relative. This insight has profound implications. It means there is no single, agreed-upon now that spans the universe. What one person considers the present may be the past or future for someone else moving at a different speed. This undermines the classical view of time as a uniform backdrop against which events unfold. In Newton's world, time was absolute. It ticked the same for all observers, like a grand cosmic clock. But in the world of relativity, each observer carries their own clock, and those clocks may disagree on what happens when. This relativity of simultaneity also affects the order of events. If two events are close together in space and time, their sequence can appear different to different observers. Suppose one event occurs on Earth and another on a spaceship traveling at high speed. Depending on the observer's motion, the event on Earth might happen first, or the one on the ship might happen first. The order is not fixed. However, there are limits. If one event causes another, that order is preserved for all observers. Cause and effect remain consistent. No one sees the result before the cause. This protects the logical structure of the universe. While time can stretch and the order of independent events can shift, the chain of cause and effect remains unbroken. This balance between relativity and consistency is one of the most elegant features of Einstein's theory. It allows for flexibility without chaos. It shows that the universe can be both strange and orderly. Simultaneity may seem like a minor detail, but it changes the way scientists understand communication, coordination, and even the nature of information. For example, in designing systems that involve high-speed travel, such as satellites, spacecraft, or particle detectors, engineers must account for these differences in time. What one sensor registers as an event may be seen at a different moment by another sensor. Precision requires understanding how time behaves under motion. This concept also informs discussions about faster-than-light travel and communication. If signals could travel faster than light, it might allow information to arrive before it was sent, creating paradoxes. That is why special relativity sets the speed of light as the upper limit for any causal influence. It preserves a consistent order of events across all frames of reference. Philosophically, the relativity of simultaneity raises questions about the nature of the present moment. If there is no universal now, then what is the present? It becomes something local, defined by each observer's motion and location in space-time. This means the universe does not evolve as a single, unified snapshot. Instead, it unfolds differently for every path through space and time. Einstein's ideas did not destroy the concept of time. They expanded it. They replaced the rigid structure of classical physics with a more flexible, more accurate model. They showed that time and space are not containers in which things happen. but participants in the unfolding of events. This change in perspective requires a shift in intuition. People are used to thinking in absolute terms, but in the realm of high speeds and large distances, intuition can mislead. Mathematics and experiment reveal a deeper reality, one that is consistent, even if it seems counterintuitive. Einstein once remarked that common sense is the collection of prejudices acquired by age 18. In the case of time, those prejudices include the idea that everyone agrees on what is happening when. Special relativity gently corrects that idea, offering a view that is more complex, but also more beautiful. It tells us that time is not a universal drumbeat. It is a pattern of rhythms, different for each traveler through space. And the harmony of those rhythms, though subtle, is real. Simultaneity is just one note in that harmony, but it is essential. It reminds us that truth in physics is not always about what seems obvious. It is about what can be tested, measured, and understood through careful reasoning. In this way, Einstein's theory deepens our understanding of reality. It invites us to see time not as a straight line shared by all, but as a web of interwoven paths, each shaped by motion, position, and perspective. Chapter 8: Space-Time, the Fabric of the Universe. By the early 20th century, Einstein had already transformed the way people viewed motion, time, and space. But special relativity was just the beginning. It explained how observers moving at constant speeds experience time and space differently, but it did not account for gravity or acceleration. To address these limitations, Einstein continued his journey. His next step was to reimagine space and time not as separate, static entities, but as part of a single, dynamic whole, a four-dimensional fabric known as space-time. In classical physics, space was the stage and time the ticking clock. Together, they provided the backdrop for all motion and interaction. Events happened in space, and they happened in time, but the two were thought to be unrelated. Einstein changed that. In his new model, space and time were not separate dimensions, but aspects of one unified continuum. Every event in the universe, every step, every flash of light, every heartbeat, could be described as a point in this four-dimensional structure. These points were called events, and they had both a position in space and a moment in time. The idea of space-time offered a new way of thinking about movement. Instead of objects simply moving through space, they moved along paths through space-time, called world lines. These paths traced an object's history from one moment to the next, and their shape depended on the object's motion. A person standing still would have a world line that stretched straight upward through time. A moving object would trace a tilted path, and objects moving at different speeds would carve out different trajectories. This new framework allowed scientists to describe motion, acceleration, and interaction with elegant precision. But space-time was more than just a coordinate system. It had structure. It could be curved, It could be shaped by mass and energy, and that curvature Einstein proposed was the true nature of gravity. This insight became the foundation of general relativity, Einstein's next major theory, published in the year 1915. According to this theory, gravity is not a force pulling objects together in the traditional sense. Instead, massive objects bend the space-time around them, and smaller objects follow the curves of that geometry. Imagine a stretched rubber sheet. Place a heavy ball in the center, and it creates a dent. Roll a smaller ball across the surface, and it curves around the dent, drawn inward not by a force, but by the shape of the surface. This is a simple analogy for what happens in space-time. The sun, for instance, creates a deep well in the space-time around it. The planets follow curved paths, called geodesics, through this distorted space. What we perceive as gravitational attraction is simply the natural motion of objects through curved space-time. This model explained many phenomena that Newton's theory could not. One famous example was the orbit of Mercury. For years, astronomers had noticed that Mercury's path around the Sun did not match predictions based on Newtonian gravity. It wobbled slightly, in a way that could not be accounted for. Einstein's equations of general relativity explained the discrepancy perfectly. Another example was the bending of light by gravity. If gravity could curve space-time, then even light, though massless, should follow that curvature. In 1919, an expedition led by Sir Arthur Eddington observed starlight being deflected as it passed near the Sun during a solar eclipse. The measurements matched Einstein's predictions, providing one of the first experimental confirmations of general relativity. This marked a turning point. Space-time was no longer just a mathematical tool. It had physical consequences. It could bend, ripple, and evolve. It became the very fabric of the cosmos, responsive to matter and motion. The equations Einstein developed, known as the Einstein field equations, describe how matter and energy influence the curvature of space-time. These equations are complex, but their meaning is simple and profound. Mass tells space-time how to curve, and curved space-time tells mass how to move. This feedback loop creates the structure of the universe. It governs the orbits of planets, the behavior of stars, and the expansion of galaxies. It even influences the passage of time. In regions where gravity is strong, near a massive planet or a black hole, time runs more slowly. This phenomenon, called gravitational time dilation, has been measured with atomic clocks on airplanes, satellites, and mountain tops. Space-time also allows for the possibility of extreme objects like black holes, regions where the curvature becomes so steep that nothing, not even light, can escape. These predictions, once considered speculative, have now been confirmed by observations. Astronomers have detected the signals of merging black holes and even captured images of their shadows. Another implication of curved space-time is the idea of gravitational waves. Ripples in the fabric caused by accelerating masses. In 2015, scientists detected these waves directly for the first time using the LIGO observatory. The source was a collision between two black holes over 1 billion light-years away. The waves passed through Earth, stretching and squeezing space by tiny amounts. This confirmed a century-old prediction and opened a new window into the universe. Space-time, once an abstract concept, had become an object of study. It had properties. It could vibrate, deform, and carry information. It was not just where things happened, it was part of what made things happen. The shift from absolute space and time to curved space-time was more than a scientific advance. It was a philosophical transformation. It forced people to reconsider what it means for something to exist, to move, or to change. It blurred the line between geometry and physics, between the map and the terrain. Einstein's space-time is not just a backdrop. It is an active participant in the dance of the universe. It interacts with everything: planets, light, atoms, and even the ticking of clocks. And it reminds us that reality is not always as it seems. Beneath the surface of motion and gravity lies a deeper structure, quiet, invisible, and precise, shaped by energy, molded by mass, and revealed through thought. Chapter 9: Black Holes, Wormholes, and Cosmic Mysteries. The more scientists explored Einstein's theory of space-time, the more it revealed. His equations, so elegant and compact, began to hint at some of the most astonishing phenomena in the universe, regions where the rules of space and time stretch, twist, and even break down. Among these were black holes, wormholes, and the vast mysteries of the cosmos. Black holes are perhaps the most dramatic prediction of general relativity. Imagine a star many times more massive than our Sun. Throughout its life, the star burns hydrogen into helium, producing heat and light. This energy pushes outward, balancing the inward pull of gravity. But when the fuel runs out, the star can no longer resist its own weight. It collapses. For small stars, this collapse ends in a white dwarf or a neutron star. But for very massive stars, the collapse continues until nothing is left to stop it. The matter is crushed into an incredibly dense point called a singularity, surrounded by a boundary known as the event horizon. This is a black hole. The event horizon is the point of no return. Once anything, light, matter, or even information, crosses this boundary, it cannot escape. The escape velocity exceeds the speed of light, which means not even photons can get out. To an outside observer, the black hole is perfectly black. For years, black holes were seen as mathematical curiosities, but gradually, evidence for their existence began to mount. Astronomers observed stars orbiting invisible companions, the only explanation being a massive, unseen object.
They detected X-rays from matter spiraling into compact regions. They even caught gravitational waves from black hole collisions. In 2019, an international team released the first direct image of a black hole's shadow captured by the Event Horizon Telescope. The object, located in the center of the galaxy M87, appeared just as general relativity predicted. A glowing ring of light surrounding a dark core. It was a triumph of theory and observation. Black holes also teach us about the limits of physics. At the singularity, space-time becomes infinitely curved. The known laws of physics break down. Quantum effects, which govern the behavior of tiny particles, must be considered. But general relativity and quantum mechanics do not yet fully agree. This conflict points to an unsolved mystery: the need for a theory of quantum gravity, a framework that unites Einstein's geometric vision of gravity with the probabilistic world of the quantum. Many researchers believe that solving this puzzle could lead to new discoveries about the birth of the universe and the true nature of reality. Among the more speculative outcomes of general relativity are wormholes. A wormhole is a hypothetical tunnel through space-time connecting two distant points. It arises naturally from Einstein's equations, though under very specific conditions. If one could keep the wormhole stable, prevent it from collapsing, it might allow for shortcuts across vast distances or even links between different times. The idea is captivating. A traveler could enter a wormhole in one part of the galaxy and emerge in another, bypassing years of spaceflight. In theory, wormholes could even enable time travel. But there are problems. First, creating or stabilizing a wormhole would require exotic matter, a form of material with negative energy density. This has never been observed. Second, even if wormholes exist, they might be too small, unstable, or dangerous for use. At this point, wormholes remain in the realm of mathematical exploration and science fiction. Still, they offer a glimpse into the flexibility of space-time. They remind us that the universe may hold structures and connections beyond what people can currently observe. Black holes and wormholes are not the only cosmic mysteries hinted at by relativity. Einstein's equations also describe the evolution of the entire universe. In the early 20th century, scientists believed the universe was static, but the equations suggested otherwise. Space-time could expand or contract. It was dynamic. In 1929, astronomer Edwin Hubble provided observational proof. He showed that galaxies were moving away from each other. The farther away they were, the faster they receded. This implied that the universe was expanding. Reversing that expansion pointed to a beginning, a moment when all space, time, matter, and energy emerged from a single, incredibly dense state. This became known as the Big Bang. The Big Bang theory raised new questions. What caused the expansion? What existed before it? What is the ultimate fate of the universe? Einstein's equations offered paths forward,
but also left gaps. One such gap is the nature of dark energy, a mysterious force that seems to be accelerating the expansion of the universe. Another is dark matter, an unseen substance that appears to hold galaxies together through its gravitational influence. Neither dark matter nor dark energy is well understood. They cannot be seen directly, but their effects are measurable. They may account for more than 95% of the total mass energy content of the universe. Yet their true identity remains unknown. All of these mysteries, from black holes to dark energy, emerge naturally from the structure of space-time. They are not inventions or guesses. They are consequences of the theory Einstein built over a century ago. In this way, general relativity is more than a description of gravity. It is a doorway into the deep architecture of the cosmos. It shows that space is not empty, time is not simple, the universe is not static. All are part of a living, evolving whole. Einstein himself was amazed by what his equations revealed. He once said, "The most incomprehensible thing about the universe is that it is comprehensible." Through careful thought and observation, people can peer into realms far beyond the senses, discovering objects that bend light, trap time, and reshape the cosmos. Black holes and wormholes may sound fantastical, but they are part of a consistent, tested, and deeply mathematical view of the universe. And though much remains to be discovered, they remind us that the universe is far richer, stranger, and more beautiful than it first appears. Chapter 10: Einstein's Legacy and the Future of Physics. In the span of just a few decades, Albert Einstein transformed humanity's understanding of the universe. With his theories of special and general relativity, he redrew the boundaries of space, time, mass, and energy. He showed that reality is not fixed and absolute, but relative and flexible. A fabric shaped by motion and matter, curved by gravity and woven with light. But Einstein's legacy is not only in what he discovered. It is also in how he discovered it. Unlike many scientists, Einstein worked not in laboratories filled with instruments, but in the quiet spaces of the mind. He relied on thought experiments, simple, imaginative scenarios that revealed deep truths. He wondered what it would be like to ride alongside a beam of light. He imagined clocks ticking in motion and observers watching lightning from trains. These insights, grounded in careful reasoning, led to breakthroughs that reshaped the foundations of physics. His work did not end with relativity. Einstein contributed to the development of quantum theory, though he remained deeply unsettled by its implications. He famously rejected the idea that nature was governed by probability, saying, "God does not play dice with the universe." Yet the very science he helped inspire moved in that direction. As quantum mechanics blossomed in the early 20th century, it introduced uncertainty, duality, and randomness at the smallest scales. Particles behaved like waves. Outcomes could not be predicted, only calculated as probabilities. This world seemed at odds with Einstein's vision of a coherent, deterministic universe. Still, Einstein's influence remained. He pushed for a deeper understanding, a theory that would unify gravity, electromagnetism, and the forces of nature into one elegant structure. This dream of a unified field theory became his lifelong quest, though it was never completed. Today, physicists continue that search. The universe, as it is now understood, runs on two powerful but separate theories. General relativity governs the large, the motion of planets, the structure of galaxies, the bending of space. Quantum mechanics governs the small, the behavior of atoms, particles, and the fundamental forces of nature. Both theories work incredibly well in their own realms. But when the very large and the very small come together, such as inside black holes or at the moment of the Big Bang, the equations break down. To understand these extremes, a new theory is needed, one that blends gravity and quantum physics into a single, consistent framework. Several candidates have emerged. String theory proposes that all particles are tiny vibrating strings, and that the universe has more than the familiar 4 dimensions. Loop quantum gravity attempts to describe space-time as made of discrete loops. Quantum field theory and holographic principles offer other approaches. Each holds promise, but none has yet achieved the success or simplicity of Einstein's theories. Still, the work continues. Einstein's influence stretches beyond equations. His approach, clear thinking, deep curiosity, and a willingness to question assumptions, continues to inspire generations of scientists. He showed that great leaps of understanding begin not with advanced tools, but with bold questions. His legacy also touches the broader culture. Einstein became a symbol of genius, but he remained deeply human. He played the violin, he questioned authority, he spoke out against war, nationalism, and racism. He supported civil rights, embraced pacifism, and advocated for global cooperation. Even as he pursued the most abstract aspects of the cosmos, he remained grounded in a moral vision. He believed that science should serve humanity, that knowledge must be paired with compassion and responsibility. This blend of intellect and integrity made Einstein a figure of global respect. His image, wild hair, thoughtful eyes, a playful smile, became iconic. But behind the image was a thinker who never stopped wondering, never stopped searching. The questions he asked still echo today. What is the true nature of time? Why is the speed of light constant? What lies beyond the edge of the observable universe? Are space and time fundamental or emergent from something deeper? What connects gravity and quantum mechanics? These questions are not just scientific, they are philosophical. They touch on the structure of reality, the origin of existence, and humanity's place in the cosmos. Einstein showed that it is possible to explore these questions with rigor and imagination, that the universe, no matter how vast or strange, can be understood if one is willing to look closely and think deeply. His theories continue to guide satellites, predict eclipses, model galaxies, and shape the technologies of tomorrow. From GPS systems to particle accelerators, from gravitational wave observatories to space telescopes, Einstein's equations are everywhere. Yet his greatest contribution may be the spirit of inquiry he embodied. He once said, "The important thing is not to stop questioning. Curiosity has its own reason for existing." That spirit lives on in every researcher who asks why, in every student who dares to think differently, and in every quiet moment of wonder. As physics moves forward, building new theories and exploring new frontiers, Einstein's legacy will remain, not as a fixed doctrine, but as an open door, a reminder that the universe is knowable, that truth is discoverable, and that imagination is a path to understanding. From the apple falling in Newton's garden to the ripples of space-time detected across galaxies, the journey of discovery continues. And at the heart of that journey, the questions first asked by a curious mind still light the way.